Afternoon, everybody. What we're going to be talking about today is it's your design. It's not just moisture management. It's air tightness. Without air tightness, your insulation really doesn't work as it should. It really is key to the overall build. You have quite an interesting climate in Romania. It's not dissimilar to mine, actually. So this is some information that we've been working on, looking at your 5 different climate zones. And I have to say, minus 24, 0 degrees is cold for me. Minus 24 really is cold. But the UK does have some... Does this look familiar? Our temperature differences are not as great, but in the summer the rain is warm, and in the winter the rain is cold, basically. So the problems that we face are very similar to the problems that you face as you build, as you create buildings which are far more energy efficient. Now, I'm pretty sure you will all be familiar with the nZEB requirements for primary usage energy into the building, and you have your different zones, and for refurbishment and for existing buildings. I have picked specifically on residential buildings, your house, my house. We could be here for days if we were talking about every single opportunity that you have. So you can see how you are allowed with existing buildings, and I think you've touched upon this with doing older buildings. You have to work with what you've got. And so there has to be some tolerance for some increases somewhere, as opposed to new buildings where you can design in the optimum solution. It's much, much easier to do, obviously. So when we look at some of the solutions that we actually have, I've just pulled together a couple of examples of different systems that we commonly see. Because, of course, with walls, you can see you're having to hit 0.25, which is fine, and with roofs, and I think that's pitched roofs, flat roofs, you name it, that's actually where we are. Now, my colleague, Attila here, has done some calculations for us. I believe you're familiar with this software, nothing unusual here. What we're actually showing you is what you build, what you design and what you build are not necessarily exactly the same thing. So this particular case, this build-up, I understand is reasonably common, this part of the world. And you'll notice that the system, number 3 there, has a very good air and vapor control layer, which is very nice, actually. You can see your U values are good. The air and vapor control layer, reducing condensation, not to a satisfactory level. 0 is always satisfactory, obviously. But the one thing that the calculation doesn't take into account is the introduction of moisture. So you can see when you have your ideal thermal conductivity, obviously that's great. As you start to add moisture into the build, it becomes more conductive. You start to lose more heat. So what you've actually designed doesn't necessarily replicate itself in the real world. And the calculation can show that. This calculation now, we have taken out the air and vapor control layer. I do like this software, really graphical. You can physically see. Now, I'm going to try a button here to see if this actually works. When I say a lovely bit of moisture, as an example, it's great. But in your build, it's not good. And if your insulation gets wet, the thermal conductivity is increased. The building doesn't perform anything like it should, and of course, you introduce a problem of condensation. The more condensate which forms in the insulation, the worse the conductivity, and what I would call the performance gap. What you've designed, what you've got, two very, very different things. I'm sure you're familiar with all of this, obviously. But when it comes to which air and vapor control layer do you need, I quite like this picture. You've stepped out on a morning, probably more in London than here, actually, getting that wet. Your shoes are dry, your socks are dry. As soon as you stand in a puddle, what do you feel? You feel the cold, yeah? So your socks, your insulation are not performing as they should, and your feet are wet at the same time. Now, if you put that into a building, as opposed to your shoes, this is the result of uncontrolled moisture. I suspect this particular image you see, I think this is some refurbishment work where that's not good, but that's probably an existing layer of insulation, may not be very good. This is a new build, I think. Insulation here, not a problem, but that is a thermal bridge. That's absolutely massive. You really don't want to be seeing that in your build, obviously. So let me give you an idea of, this is where the onus is on you as designers, really. You need to look at your building and decide which form of air and vapor control layer do you need. Now, it could be a relatively low SD value air and vapor control layer. You could argue more of an air leakage barrier with sufficient vapor resistance for a domestic building. Not a problem. It may be that your building requires something with a much, much higher SD value. As an example, if you were building a swimming pool, a fairly obvious one, an awful lot of very warm water producing an awful lot of moisture. Notice the batten space, which is much better from an air tightness point of view. Or it may be something you're looking at, it's a product with a variable SD value. Some advantages here, depending on your build, but all of these rely on adequate sealing. You would be amazed the number of times I am asked, I am using your name of product, do I need to seal the lap? On an air and vapor control layer, a non-sealed lap makes the whole thing, it's a nonsense, it's a farce. So sealing the laps, dealing with penetrations, and a big problem I find, you make a lovely airtight envelope, somebody else comes along to fit. I won't single out electricians or plumbers or anything. They make a hole and they cover it. That is a huge air leakage point, and that's where the moisture goes. Doors and windows, we can make a box airtight, but we don't live in boxes. We have doors, windows, luckily, and they need to be sorted out. They are key. And sometimes there are flexible approaches, which make life an awful lot easier. With a little bit of practice, one product can seal a round pipe of any size, a door, a window, you name it. While I've got that there, I've got two case studies to show you, but I think we've got a live case study right here, right now. When I came in the door this morning at about 10, it was reasonably warm. The humidity was perhaps 40, 50%. You're all sat here now. Can you all feel the humidity in the air? It's something you can feel. It's not impossible. The reason I say that, when I walked in this morning, relatively low relative humidity, it's now considerably higher. How do you design for that? Which one of these products do you actually need? I will reveal the answer at the end. But one thing I really recommend, specifying a product, reading about a product, the best thing you can do is to practice what you actually preach. Do it yourself. Lots of hands-on training, really recommend this. Once you get a feel for a material, you can see the difficulties of dealing with corners, with windows, whatever it may be. Yeah, that's the best way. Practice what you preach. In my opinion, that's the best route to success. Because if you don't practice what you preach, this is quite an interesting, fairly local example where an attempt has been made to form an airtight lining. Unfortunately, what they've done is to put a non-permeable layer, which goes from the warm side of the insulation, the correct side, on top of this timber material, this rafter. So now you have an impervious layer on top of that rafter. Where does the moisture go? Huge thermal bridge, not helped by the fact you have a non-permeable underlay. My little pointer's disappeared, there it is. This doesn't help. You need vapor resistance warm side, vapor permeability on the cold side, be that in a pitched roof, be it in a wall, wherever it may be. Quite shocking, really, when you look at that video. This is where a variable vapor resistance AVCL comes in, because you get a benefit year-round. When it's applied to a dry structure, the material itself is vapor resistant. That's absolutely fine. That might be in your winter condition. When you then move through to the summer, where your vapor drive may now be from external into the building, the ability to reduce its vapor resistance is key, and that's the secret of success. in actual fact. And this is a fairly typical graph of some products that we see, where you can see as the humidity actually increases, the material itself is able to change state, which is nice, allowing any trapped moisture to escape into the building. And because you're making airtight buildings, you can control that with ventilation rather than leakage, and it takes care of the moisture internally, which is a nice feature. You get the benefit of airtightness and vapor control year-round. It's not just a winter benefit, it is a year-round benefit. So 2 case studies, real case studies. The first one, and I'm pretty sure you would have seen this on the TV, used a combination of metal frame and timber frame with a variable vapor resistance air and vapor control layer, and also a breathable layer on the external face to keep the building dry. These were fairly typical types of details that we see. And I'm pretty sure if I show you this picture, are you familiar with this building? Grand Designs, I think you do see Grand Designs. Hell of a job to get this actually built. A combination of factors went into it. I was involved quite heavily with this particular application. Really, really nice building. This was taken probably 6 months after completion. And this week on the TV at home, they showed this as a revisit. This building has never once had an ounce, 1 gram of energy put into it to keep it warm in the winter. Nothing. 0. That's to do with the air tightness, which protects the insulation, so the insulation performs as designed. Another small example for you when I'm involved with Scotland for me is this Tuesday coming, which is a bit of a punch from home. Not a passive house, but built to passive house type standards, 0.6 air changes. One of the pupils here was at this school, was a little bit upset about something. Probably his homework was late, I imagine. He decided to set fire to the place, which is not good, obviously. This is what is actually going in its place. Quite nice, nice structure. And we've spent a lot of time on site actually making the building airtight. Now, this section that they conceal with this type of build, quite airy, quite nice, less than 0.6 of an air change. So this particular building will have minimal heat input. 2,000 children running around is more than enough to keep that building warm. I'm absolutely convinced. So what we would recommend you use, if you're not familiar with the term fabric first, you have your structure, you have your required insulation, make it work as it should, make the building as airtight as you can. You then control conduction, convection, and radiation in one. And if you can make a building that physically requires no heat input, you can see that it really is well worthwhile. 32 seconds left. I'm almost bang on time. If we get it right, you will no longer need our little friend here to do the splits in front of the door. You're not going to be required. And in summary, if you build tight but ventilate it right, not have a leaky building with air, something you control, quite a difference. Early engagement to get the right material, to do the right job in the right location, absolutely 100% key. Calculate the risk. You've seen the calculations that you do. Or why don't you speak to an expert who will do the calculations for you? Last thing I'm going to say, 15 seconds over, think twice, but only build once.